So good evening, everybody, to the ISHRAE webinar series. This is on optimizing cooling system efficiency with distributed pumping systems in data centers. And welcome to CoOL Conclave 3.0. I would like to introduce the top four people of this CoOL Conclave 3.0. First is the chairman, Mr. Subramaniam Chandrasekhar. He is a lead fellow and carries out design consultancy in the field of HVAC&R, intelligent building management systems and sustainability, with a background of over 40 plus years of professional experience in these fields. He also served as a senior trainer in Train Academy in his previous assignments. Next, we have the vice chairman, Mr. V. Sridhar. He is a first generation entrepreneur with an extensive experience in the HVAC and refrigeration industry, known for his technical expertise, leadership, and business acumen. He is also actively involved in the skill development, conducting HVAC training programs for engineers and hands-on training in air conditioning service and maintenance. We have a convener for CC 3.0, Mr. Seshadri Kattai Rangasamy. He has over 40 years of experience in the HVAC industry and is a certified energy professional. He is currently providing consultancy service and performance auditing under the name and style of Mrs. EnerSafe Solutions, operating across India, Africa, Asia, and Middle East. Finally, we have the co-convener, Mr. Sendil Raj. He is a seasoned HVAC principal consultant with over 30 plus years of hands-on industry experience, known for his deep technical expertise, dynamic leadership, and result-driven MEP solutions. He has successfully engineered and delivered complex HVAC systems across healthcare, academic, commercial, and industrial projects. Now I'll play the video of CoOL Conclave. Check on.
Yes.
Check on, waiting for your update.
Am I audible, sir?
Yeah.
Hello. Manish sir, can you please stop your screen sharing so that I can play the video? Maybe the technical.
Okay.
Kindly let me know if video is functioning properly.
Get to see the screen, Jayant.
Yes, sir.
Yet to see the screen. I mean, we're not seeing the
Nothing
videos.
has come up.
Yeah, or
Sir.
your screen. You can see the screen.
Is it functioning, sir?
But not the
Yes.
audio, but video is.
Audio is not clear. Audio is not functioning. Just give me 1 minute, sir. The sound is functioning, sir?
No.
Negative from my side. And are you trying one more time? Can we move forward?
Yes, sir. I'm trying from my end.
But try once. If not, we can move forward.
Just give me 1 minute. It sound clear, sir?
No.
No, I think you let the video run. I think it's a challenge on the video audio part.
Maybe
Right.
it is a technical glitch. Let
Right.
let me allow to play the video.
Yeah, please play the video and get it done so that we can move forward.
Thank you, sir. Lisa,
So, I'll give a small brief about the speaker. Dear participants, please join me in welcoming our dynamic sales leader and inspiring changemaker, Mr. Manimaran. It is a pleasure to welcome Mr. Manimaran, a dynamic sales and business development professional with 15 plus years of experience in the mechanical and industrial engineering industry. With strong expertise in project sales and key account management, OEM sales, channel management, and product and solutions development. He has successfully introduced innovative solutions into new markets and consistently driven business growth. Known for his proactive approach and strong customer relationship management, he continues to create value for clients, consultants, and organizations alike. Welcome, Mr. Manimaran. I give the floor to you. You can start your presentation.
Thank you, Mr. Manish. Let me know, am I loud and clear in first place?
Yes, sir.
Good. Let me know when you can see my screen.
Yes.
And there's just a single screen that it's visible now, right?
Yeah.
Good. Thank you, Mr. Manish. Thank you, Mr. Jaykant, for the welcome note and setting the tone for today's webinar. Very good evening to the industrial experts and audience who joined today for this webinar. Thank you to ISHRAE for conducting this CoOL Conclave session and giving us opportunity to present. My name is Manimaran. As Mr. Manish introduced, I'm handling the data center business across India, Middle East, Africa, based out of Dubai at Grundfos. Today, I'll be talking about how we can optimize cooling system efficiency in data center using distributed pumping system, a concept that is becoming increasingly relevant as data center capacity and complexity grow. I hope this session will definitely bring value addition in terms of technical to all the audience and participant today. And in case if you have any questions, I sincerely request to put it in the chat box. And at the end of the session, we'll try to address that during the Q&A session. Let's start. So data center cooling. So the data center industry is witnessing unprecedented growth, largely driven by AI, machine learning, cloud computing, and high performance computing. So for addressing in the modern needs, we need a GPU with high capacity, high processing power, but it comes as a cost. The power what GPU consume and the heat what it emits is always a challenge to do a cooling which the heat has to be taken away from the GPU. So the cooling capacity what we are seeing today because of the modern advancement in GPU is tremendous. If we go back a year back and see what is based on the GPU what was available at that time, and if we see the density of the server rack, we used to talk about 13 to 17 megawatt per server. So to remove the heat of such capacity, the traditional air cooling technology was doing a wonderful job. But seeing the growth and the capacity of GPU and amount of heat what we need to remove from the system and from the server today, the air cooling technology is no more efficient. So we need to see what are the alternate method where we can make the system more efficient, at the same time removing the heat and delivering the performance for the system. So, in today's technology advancement and the challenge, we have to see a different way of approach for addressing these needs. And that's how the hybrid system, which is comprise of air cooling technology and water liquid cooling technologies, come to the picture. And such demands needs a flexibility and scaling and efficient technology to be implemented in the as a part of a design in data center pumping system. That is where we see distributed pumping comes as a versatile solution and future ready fit for improving the efficiency at the same time managing the demand of the system. Let's see what is distributed pumping. So distributed pumping basically a shift towards decentralizing the pumps. When I say that, if you see the traditional way of pumping, we have a centralized pumping system and we distribute the water across the network. So as name implies, the distributed pumping, we are assigning the pump to address the need of each load. So no more centralized pump. We are decentralizing the pumps to each node to address the need of that node in a better way. And this is an alternate method compared to what we are doing today to distribute the chilled water in data center environment. Before jumping into this, let's see how we define the efficiency in data center. PUE is something a benchmark for data center efficiency that we all know. Power usage effectiveness. What is that? It's nothing but energy used by computing equipment and the support infrastructure like cooling, which defines this metric. Now, coming back to a chill water system and the pumping system, by removing energy consuming component and still maintaining the efficiency and addressing the demand will improve drastically the PUE of the data center. In chill water system, a modulating valve is traditionally the way to control the flow in the system, right? Which in turn control the cooling flow. So that's how traditionally we've been doing a chilled water distribution and addressing the cooling load for more than a decade or even for more than a couple of decades. But when we see a valve, when it gets throttled, it creates a back pressure, which requires more power because it adds head to the pump, which requires more power and it consumes energy to overcome this back pressure. That's as a part of a traditional design what we see today. If we can control the flow without the valve, then we are eliminating the unnecessary pressure which is created in the system, which is added as a pump head, and in turn it consumes energy. So that's what we are trying to do with respect to distributed pumping. So it's basically we are trying to change two fundamentals what we are doing in a traditional system, removing unnecessary modulating valves wherever it is feasible, which means today we are having a valves to balance and modulate the flow in closed loop system. That is what we want to change. The unnecessary friction which is created in the system to do this function can be done in much better way by removing this unnecessary friction which is created by the valve. And the second major challenge which we see in any closed loop system is how do we balance better the primary and the secondary side of the closed loop system. So when we say primary, which is the source where we produce chilled water through chiller, and we have a distribution side where we need to distribute the chilled water to each load. The balancing is something primary which makes the system more efficient. So the delta T of the primary and secondary has to be managed and matched to keep the plant room efficiency to closest to the most efficient way. These are the two critical components what we see in a traditional design of the system, and these challenges are addressed with the help of distributed pumping. So what is the direct benefit? We are improving the pump energy, pump efficiency by reducing the energy consumption, and at the same time we are improving the efficiency of the total system. So this innovative cooling approach is not only helping to save pump energy and system energy. In other way, the data center is a application where we have to keep adding the module when the load get increases. Distributed pumping is bringing a flexibility of adding module whenever your load get increases. That's the additional advantage what distributed pumping kind of design can bring and add value to the data center design. Let's go into detail when we see the system design. So before starting the details of the design, let's see what are the straightaway advantages that we can expect from distributed pumping vis-a-vis the traditional conventional variable primary or fixed primary variable secondary system that what we do today. Simplified design process. When we say simplified design process, let's give a thought about how we design a system today. So we have a centralized pump, as I said, it can be a primary variable or it can be fixed primary and variable secondary. So this drives the flow across multiple load which is connected in the closed loop system. What is challenging? to identify what is the exact changing in demand is always a challenging thing to identify. So in today's design process, how are we doing it? Are we addressing the flow requirement based on temperature feedback? No. So we are doing it in a way, it's an indirect way of identifying the flow, which is a pressure based system. So we modulate the system based on the temperature requirement on the load side, and that is translated to the valve. And when the valve functions, valve moves, it creates a differential pressure. We have to identify which is the critical load. We place the DP sensor or differential pressure sensor and take that feedback to the primary pump or secondary pump to distribute the flow. So the design of the system is little complex. It's not direct, it's indirect way of doing it. And decoupled system reduce the need to determine the critical index flow. So when we decouple the primary and secondary and have two different sources or driver, it is very easy to determine where we are having the critical load and addressing that critical load. So these are some of the advantages that what we can see and make it easy in distributed pumping. And modular design. So as I said, data center needs a modular approach. So the data center progress when you have more load which is getting into this added into the server. So even our design is modular. When the load get added and we can add our the source and driver, that makes a system more little complex and more efficient and more flexible to operate. And as I said, the conventional system operates based on pressure. We monitor what is the differential pressure across the critical load or furthest load, and based on that feedback, we try to modulate the flow, which has been distributed across various load connected in the system. Is that a right way of doing it? Yes, but there are better way of doing it. So the actual flow has to be controlled, understanding the temperature need of each load, and that's where we are moving with the distributed pumping. And this is something which is very critical. Balancing. Being a closed loop system and centralized pumps need a good balancing approach to make that system to be efficient. Now, how we do that? So we do that with the help of valves today. So we have balancing valve at each unit level, and we try to balance the flow based on the capacity or based on the need of that particular unit. What happens if the balancing is not proper in the system? The entire efficiency of the system has been compromised. So balancing is always a critical parameter or functionality in a closed loop system, and it's not one time. It has to be maintained throughout the operation of the system to make the system more efficient and to address the temperature of each unit. This is a little complex, and this has to be managed every time in the system in a traditional way of design. That's what we are trying to address. We want the system to be self-balanced. And with distributed pumping, and with the kind of pumps connected to each load, that's very well possible. We are clearly decoupling primary and secondary, and we connect a dedicated pumps to each node. By doing that, the system will become a self-balanced system, and we are moving out of manual balance system. And these are clear advantages that what we are trying to add with the distributed pumping on top of the conventional system what we have today. Let's see in a little bit in schematic so that we have better understanding. So let me pull out the pointer. So it's a simple SLD for the benefit of discussion. So we have a chiller, which is a primary circuit, a pump which is driving the flow into the chiller. So the red line is written from the load from the data hall, and then the water gets into the chiller, and then the supply water from the chiller gets into the data hall. It's a pretty basic design, and assume these are the loads. Let's say it can be a fan wall unit, or it can be a CRAW unit, or it can be a CDU, cooling distribution unit. The chilled water from the source, from the production loop, is pushed into the distribution loop, which is the secondary side of the system. And if you see, the individual unit has to be balanced with the help of balancing valve, and further to modulate the flow based on the change in the load on the unit level, we have a valve which is a actuator based modulating valve which modulate the flow based on the load variation and that particular load. So this is a very typical design that what we see today. And how does the functionality happens? When there is a change in the load, the feedback from the temperature sensor of the air side is given back to the valve, and this valve modulate to manage the flow, which is pushed by the pump, a centralized pump from your plant room. That's how we distribute the flow to multiple units connected in the secondary side. And we capture the differential pressure, the back pressure created by the valve when it is moving up and down, and that feedback is given back to the centralized pump, and the flow is being modulated. So if there is more load, the valve opens, and the differential pressure go high, and that feedback is given back to the pump to increase the flow. And vis-a-vis on the reverse side, when there is a less load, the valve closes and the back pressure varies, and that feedback is given back to the pump to reduce the flow. It's a pretty simple system. That's how we operate a variable primary system or variable secondary system. So as I said, the balancing and modulating valve plays a major role in terms of balancing the flow to each unit and modulate the flow based on the change in load of each unit. The moderating valves regulated based on the feedback from the temperature sensor, and that creates the flow difference across the load based on the feedback from the temperature sensor. So what is the challenge that we see here, and what is that we need to overcome from the design that we propose? When we do balancing, balancing is, of course, it's a critical parameter, as I said, but it comes with cost. When we do balancing, the friction created by this valve is added as a pump head, and every time when the pump has to overcome that friction, it consumes energy, which is like driving a car by putting a brake and accelerator at the same time. And similarly, when there is a change in the flow, this valve has to further modulate. When the valve modulates, it creates further frictions, and that friction has to always compensate by the pump by consuming more power. This is something, a challenge that we see, which can be overcome by the way we can decentralize the pump and give a local control, temperature control to the pump. And on the second hand, if the balancing is not proper, the impact that it brings to the system is much bigger than the pump energy that what we are talking. If there is a delta T difference between supply and return, the chiller will experience low delta T, and that will pull down the efficiency of the chiller, as well as it will pull down the efficiency of the plant room, and it increase the PUE. So it is directly linked to the PUE, and we want to address those by changing the concept, how we are doing it today. Let's see quickly how we can give a change. So same schematic, the primary remains the same. So the pump is driving the flow to the chiller, and but the only change is the primary pump is limited for the distribution of chilled water on the plant room. So the line which you see, which is dividing the primary, which is the production loop, and the secondary is a decoupler or a bypass. So the primary pump is just designed only to cater that. And if you see, we have removed the balancing valve and flow control valve, and we have connected dedicated distributed pumps or coil pumps to each load. So now each unit or each load has its own driver, and each unit demand is addressed by its own driver. That's the difference that what we are trying to bring in the design, and this will eliminate a kind of friction created by the valves, and that is a saving that what we are seeing on the pump side. And more than that, we will see in detail how this can be, how the design can, how we have to design the system, and how we need to put it in the automation so that the savings and on both pumps and system level can be seen. So as I said, by removing the valve, what we are doing is pretty simple. We are just removing the pressure which is created by the valve, and that's straight away savings. And we have a dedicated unit, a decentralized pump, a coil pump connected to each unit. And now the commissioning is very easy because we are moving out of a manual balancing. See, these systems are self-balance system. We can just connect the pumps, start the pumps, and there is no, absolutely, the system will balance by itself between the primary and secondary, which we will see in a moment. And this can be very well adopted for the existing system. It can be a primary variable or fixed primary or variable secondary. Both the system can be retrofitted with distributed pumping or the coil pumping or the decentralized pumping, whatever terms that we use. It's more easy to adapt in greenfield project as well as in an existing project. The retrofit is much easier, and we can really see a good payback, and it eliminates a lot of complexity what we see in today's design. Let's get into a little more detail. Let's start with variable primary system, which is the most efficient system that we have in today's design. This design is pretty energy optimized design compared to primary secondary, fixed primary variable secondary. But let's see how we need to, what we need to adapt in terms of designing variable primary to distributed pumping, and how control philosophy will change, and what is the kind of design change that we need to adapt, and what is the saving that we can expect in tune of percentage. Let's get into the detail of the design. So let's see the primary variable design first before moving to distributed pumping with variable primary as a concept. So the variable primary pump, the pumps are designed for the capacity of chiller. It can be one pump to one chiller, or it can be a common headed system, and the flow is equated based on the tonnage of the chiller. And the head of this pump is based on the friction from the pump till the entire load, maybe a critical load or furthest loop back to the pump. So that's how the head of the pump is being calculated in a conventional design. And moving towards the secondary side, we have multiple individual units. It can be CDU, it can be fan wall unit, or it can be CRAW unit connected with modulating valve and balancing valve. And that's how the system on the secondary side has been designed. And as I said, this system is a pressure driven system. So when there is a change in flow based on the movement of the valve, the back pressure at the critical load or further slope is being monitored, and that is given as a feedback to the pump to move the flow up and down. That's how we understand the requirement of change in load on the secondary side, and we give pressure as a feedback to the primary pump to modulate the flow and try to manage the demand by exactly producing and driving the flow from the primary side. And we have a little line here, which is a decoupler line, bypass line, which is to ensure the minimum flow. So any chiller comes with a minimum flow which has to be maintained, and during that condition where the load is much lower than the minimum flow of a chiller, we fix the speed of the pump not to drop below the minimum flow, and we push the flow, and exactly the flow what is needed on the secondary been taken, and the excess flow will be bypassed through the decoupler line. That's how we maintain the minimum flow to the chiller. But if that will compromise a little bit on the delta T of the chiller side. But if let's see the scenario where the balancing is not proper as per ISHRAE 90.1. Let me put this way: the valve authority is something which is a critical component or critical parameter or critical characteristic which has to be considered during design. So ISHRAE clearly defines 30 to 40% of friction of the entire friction of the system has to come from these valves. So for doing balancing and flow modulation, as per ISHRAE 90.1, 30% friction has to be added apart from the friction loss what the other equipments or the components is providing in the system, which is huge. That will be adding as a power consuming component to the pump. And if we compromise on the valve authority, the balancing will be challenged. So once balancing is challenged, then the delta T of the system gets challenged, and the efficiency of the chiller drops. Input kilowatt per ton will get dropped, and the PUE goes up. So these are the challenges that what we see in a valve-based system during the balancing and flow modulation, and that's something that we are trying to address in a distributed pumping. Let's get into the detailed design of distributed pumping. So to see the advantage and disadvantage of variable primary system, it's pretty simple. Compared to variable secondary, variable primary is having a little benefit on the capex. It saves space. It reduces power consumption because your chiller and the most of our the equipments are varying based on the demand. So we save when we vary the speed of the equipment to meet the demand, varying demand at the load side. So there is a clear advantage on this aspect, but the disadvantage, the flip side of the design is The design is a little complex because we are modulating the flow with indirect way of doing it. It's not the direct way of modulating the flow. That's one challenge. And the commissioning is always a difficult thing because balancing has to be ensured. And then we need to identify the critical load, set point of the differential pressure, and then the pump has to modulate according to all those parameters. It's always the flip side of having variable primary, and it needs a lot of um, uh, um, operational tactics to keep the system intact with respect to the efficiency. Let's see how this can be translated into distributed pumping. So the primary side still remains same. The pumps will be variable, the chillers will be variable, but the only change is the head of the pump is restricted to overcome the friction only on the production side, which is the primary side, till the decoupler line. So the primary pump head is calculated from the discharge of this pump, chiller drop, decoupler line drop, back to the pump. That's it. So it's like fixed primary, but the pumps will be variable primary. The design remains similar to the fixed primary. Coming on the distribution side, which is the secondary side. So each unit, when I say unit, it can be fan wall unit or CRAW unit or CDU, will have its own dedicated coil pumps connected to each unit. So the design of this pump is pretty simple. The flow of this pump is equated to the capacity of the unit, and friction of this pump is calculated from to overcome the friction from the decoupler, which is basically from the start of the secondary loop. Let's say the head of this pump is calculating the friction of to starting from this decoupler and the coil drop of this particular unit, any accessories, pipe frictions, and the return line back to the decoupler. That's the head of this pump. Similarly, the head of this pump is going to be the same way, taking the friction from decoupler and the particular coil drop and the accessories losses and the return line losses till the decoupler. So each unit has its own pump, own driver, where it is driving the water based on the need of that particular unit. That's why we call this as decentralizing the pump, or a coil pump which is having a dedicated pumps to each coil. Right now we have multiple way of doing it. This clearly say one pump connected to one unit, but we can have a hybrid approach, which I will show it in coming slides. But by doing this, the operation philosophy gets very simple, which I will show it in a couple of slides, how we operate or modulate the flow and how we balance the flow between primary and secondary. And same thing, still we see a bit of constant primary and variable secondary is also a more adaptable system, even in data center. And even with that concept, distributed pumping or coil pumping can be very well done. So how the design philosophy is very simple. The primary pump is fixed speed, and the primary pump is designed to overcome the friction only on the production circuit, which is the primary circuit. And we have a centralized secondary pumps. So from the decoupler, the centralized secondary pump will push the water to commonly to the multiple loads, and we have a balancing and modulating valve which balance and modulate the flow based on the change in the load. Pretty simple. Again, we have a DP sensor on the critical load or furthest index. We take that and give that as a feedback to the secondary pump, and it modulates based on the change in the load. Pretty simple design, but the same challenge what we see in variable primary is still there. And on top of it, since the primary is fixed speed, the delta T is compromised on most of the time when you have a chiller running at full speed, but your secondary, the load is much lower than the full speed of the chiller. So the energy is compromised again. Let's see how we can do this in a better way with distributed pumping. Before jumping into that, let's see how it impacts on the pump performance, or where the savings is coming from on the pump side. So when we have a valve-based system, this is the pump curve. We have x-axis flow, y-axis is your head, and this is the pump curve at full speed. This is the system curve where it starts from zero, and based on the closed loop system and based on the differential pressure across the critical load at full speed, your control curve may vary for each system, and it depends on the system, the requirement. And let's say in a conventional system, this control curve will always stay somewhere at 30 or 20% of the overall head. So that static will always be there. We cannot further modulate the pump below that static. It has to be there at the system, and the control curve follows that static. Based on that static head which we have to maintain. And that is the friction which the valves are creating, which valves are always putting into the system, and that head is added as the pump head into the pump, into pump head as a head into the pump. So the cooling liquid flow is controlled by a series of valves, increasing and decreasing the flow to meet the cooling needs. So as I said, this is a typical view of one particular load. Let's say this is a supply line from the your secondary system or primary system. The chilled water is getting into the coil, and this is the return line where we have a modulating valve which modulates the flow. The control is reliable. We achieve the temperature what we have to maintain, but at the cost, as I said. So it comes with the additional cost which we want to bring us a saving by changing the way we are approaching the system. So with the same primary secondary, the primary remains the same. With the VFD, the secondary will have its own dedicated pumps connected to each coil, and the control philosophy and the design philosophy remains the same. So now, how we are controlling the flow when we have pumps across each unit? It's pretty simple. In a conventional design, the temperature feedback is given back to the wall, but here the temperature feedback, the air temperature or return temperature feedback is given to the pump. So the pumps, which are smart pumps today, can take feedback, analog input feedback from the temperature sensor, and we can give a set point, what it has to maintain, and based on the actual feedback, the pump modulates its speed. So these pumps are smart pumps, which is available in the market, which can vary the speed as it has inbuilt drives and the controls and the sensor attached to it. So based on the temperature of that unit, the flow has been driven instantly controlled by taking the temperature feedback. And that's where we are saying the system is temperature dependent system, whereas the conventional system, valve based system, is a pressure dependent system. And modulating the flow based on temperature is more accurate, more faster, and energy efficient, and that's where we get savings on the operation side of it. So let's summarize the challenges that what we can see in a conventional system. Though it does its job, but we can still improve the way or improve the efficiency to achieve the performance what we are doing today. So difficult pain points are difficult determining the index circuit. As I said, what is the critical load? Where is the critical load? What is the differential pressure that we need to set to modulate the flow based on changing demand is always a critical thing that we see in a variable primary system or a conventional variable secondary system as well. Proper valve selection, as I said, ISHRAE 90.1 clearly defines the valve authority is something critical in design consideration. We see that is compromised in most of situations. If we compromise valve authority, then the balancing will be poor. That will impact the delta T of the system. And design performance is completely rely on how we balance the system, how we maintain the balancing of the system throughout the operation of many years. And if that is compromised, it will pull down the efficiency of the pump, it pull down the efficiency of the chiller. And further extension, the conventional system has to, if, let's say if the load has to be added at later stage, if we design the pumping system, the pumping head has to be designed for the future expansion as well at first step itself. So which is the challenge in terms of design aspects when you add a load at the further stage. So we are addressing those challenges with distributed pumping or coil pumping or decentralization of pumping. Let's see a little bit of balancing side, how we balance primary and secondary, how we control the flow on secondary side, how we control the flow on primary side. So as I said, so we have a primary loop, which is a production loop. We have a secondary loop, which is a distribution loop. The primary pumps are designed only to handle the flow within the primary loop. So we have a decoupler, which acts as a intermediate between the primary and the secondary. and the primary pump will does the job till the decoupler, and each secondary pump will take the pump chilled water or drive the chilled water from decoupler to that particular node and send it back till the decoupler. That's how we clearly define the primary and secondary side of the circuit, and each will does its job to balance the flow based on change in the load. So let's see first how we balance the secondary circuit. Distributed pumps on the secondary circuit manage the load by itself by taking the temperature feedback from the air side. So let's say we give a set temperature of 30 degree and the actual temperature is 32 degree from that particular data hall. Then the pump will increase its speed and it try to take more chilled water from the decoupler line. Whereas this load is not having any increase in the load, this pump stay off, and there will not be any chilled water which is driven by this pump from the decoupler line through this loop. So that's how we make these pumps independent and this unit independent, and the flow is modulated precisely based on the temperature feedback. That's how we modulate the flow for each unit on the secondary side. So moving back to the primary control, the primary side is controlled by a logic. It can be through a PLC, it can be through a BMS, or it can be through a CPM. So as similar like variable primary system, the chiller minimum flow is critical here. We does the same how we do in a conventional system. The minimum flow of the chiller will be maintained by locking the speed of the pump and by ensuring that minimum flow is always fed into the chiller. And if the minimum flow is met, then based on the control logic which determines what is the load on the secondary side, the primary pump flow keeps varying. It increases or decreases based on the load changing on the secondary side, which is captured with the help of temperature sensor across the decoupler, which we will see in the next slide. So pretty simple, the DP sensor, the differential pressure sensor, or the flow sensor, feedback is given back to the controller to ensure the minimum flow, and that's how we protect the minimum flow. And based on the temperature difference across the decoupler, which varies based on the secondary side, the primary pump flow is modulated by increasing or decreasing its speed. So let's see quickly how the balancing happens between primary and secondary. So as I said, this is the decoupler line. We capture the temperature across the decoupler line on both supply and return, T1, T2, T3, T4. 4 temperature sensors being installed across the decoupler line. And ideally speaking, when the system is balanced, where the supply met the demand exactly, the T1 temperature is equal to T2 and T3 temperature is equal to T4. Let's give some example. For data hall 20 and 29 is the supply and return temperature. If the load is say 100 gallons per minute and the source is 100 gallons per minute, your T1 is 20, T2 is 20, and the system is perfectly balanced, and your T3 will be 29 and T4 will be 29. This is the ideal condition where we want to keep the system. The primary flow is exactly produced and driven to match the load on the secondary side. That's how we balance the circuit. It's not a manual balancing, it's a self-balance system. What happens if there is a change in the load? If there is a change in the load, the secondary flow is little, let's say if the load increases, the secondary flow is a little higher. Let's put some number to it. The primary flow is 100 gallons per minute and secondary flow is 200 gallons per minute. The excess 100 gallons per minute will get through this decoupler line, and it increase the T2. It's supposedly to be 20, but it will increase to 21. Now, by understanding the logic of T1, T4 minus T1 and T3 minus T2, when there is a change in the load, that signal will be fed to your CPM or BMS or PLC, and that will send a signal back to pump to increase its speed. So it's pretty simple. If your secondary flow is more, it impacts your temperature across decoupler, and that feedback is given to the controller to increase or decrease the speed. That's how we balance the system. To give with some example, this is an ideal condition where your supply is 10, return is 16. Good. But let's say if the flow is more on the secondary side, the excess flow will get bypassed through this decoupler. It's a least resistance path. So whatever the primary is capable of taking based on its speed, the flow will pass through the decoupler. Whatever is excess will take this decoupler, and the temperature, ideally it's supposed to be 10 degree, now it is increasing to 11 because of the excess flow. By identifying this scenario, now the PLC or CPM will give a command to primary pump to increase the speed, and the system gets balanced by itself. On the return side or the reverse side, if there is more flow on the primary and the load on the secondary side gets reduced, the excess flow from the primary gets bypassed through the decoupler, and it impacts your T4, where ideally it should be 16, but it now moves to 15. So by identifying this scenario, we will further reduce the speed of primary pump. So it's pretty simple. The balancing can be done at any point of time by identifying this temperature difference across the decoupler. So let's see a different configuration that we can put this concept in data center. So as I said, now the hybrid cooling is picking up more, let's say 50-70 or 80-40 ratio of air cooled system and liquid cooling system. This concept can be ideal fit for both the options. Let's say if it is a liquid cooling system where predominantly it is cooling distribution unit at present. So the cooling distribution unit can be a redundant thing for a data hall, or it can be a pump level redundant. For example, the first scenario is where you have a redundancy on the CDU level for the data hall and one pump to each CDU, or we can have a common CDU and the pump can be redundant as common. And if, as I said, since the system can be hybrid, we can use this for rear door heat exchanger, or this can be used for fan wall unit, or this can be used for CRAE unit as well. The concept remains same. And even for immersion cooling, the CDU concept remains the same, and then the pumps can be either have redundancy on the pump level, or it can be on the CDU level, which you can see in the next slide. But this is another set of configuration, and this can work good for across all tier. Even if with tier 4, the distributed pumping or coil pumping or dedicated pumping can be ideal fit, and it gives us more flexibility to add load at any point of time without doing the rebalancing of the system. That's also one of the beautiful of having a dedicated pumps to each unit. So coming back to the benefits, that what we can see from the pain points, what we have discussed from the variable primary system or variable secondary system. So it will definitely reduce the pumping energy consumption, because we are removing the unnecessary friction which is created in the system, but still we deliver the same performance in much better efficient way. And since this system is a temperature driven system, the multiple complexity is being removed from the pressure based system, that will further reduce the energy consumption of the pump. The balancing becomes much easier between primary and secondary, and that will give advantage of maintaining the delta T closest to the design at most of the time. As I said, it's optimizing the delta T, which will improve the performance of the chiller, and it's a modular design. As I said, when we keep adding CDUs, or when we keep adding fan wall unit or CRAE unit, the system can build when the load gets growing. So that's the advantage that we get when we move to a dedicated or distributed coil pumping system. And it's a more efficient way of operating the system with temperature feedback rather than pressure feedback. And as a concept, this is something which is available in the as a design guideline from ISHRAE for many decades. The players have started implementing this concept as a design advantage, and it's there in the market for many years. And we have a lot of case studies across globe. And just to give you a number, what saving that it can really bring in terms of kilowatt per hour, it's the facility what I'm referring right now, it's a 3.3 megawatt facility which has a chiller as a primary device, and it has a CRAE unit and fan wall unit. It's a air cooling based system. There is no CDU in this case study. The original design suggested is with variable primary of 10 primary pumps of 30 kilowatt each with N+2 redundancy. Tier 4, an estimated energy consumption with variable primary is around 672,000 kilowatt hour. With the distributed pumping design, where we removed the unnecessary friction, and having a dedicated pumps of 66 numbers connected to each unit, and 10 primary pumps where the primary head reduces and the kilowatt reduces, which is 11 kilowatt. After adopting a distributed pumping design, the savings, the energy consumption is around 392 kilowatt 1000 kilowatt per hour, and the savings is around 271,000 kilowatt per hour, which is approximately 40 to 50% energy saving on the pumping power consumption. Apart from this, managing the delta T to a better level will pay much more efficiency on the chiller side, which will help us to improve the IKW per TR as well as reduce the PUE in total. So it's something which is implemented, tested, and we have really seen the results. And many of the data center player started implementing this in their own design. So this is something which can bring better performance for the system and at the same time reduce the energy consumption with the increased capacity in data center. Thank you so much. If you have any questions, we can, Mr. Manish and Mr. Jaykant, if you can help me with the questions, we can do that now.
Mr. Kapse,
Yes.
he has a question. In intelligent pumps, we require standby pumps in each circuit. So basically, you require n plus n pumps instead of n plus 1 pump.
Okay. The answer to that is okay. With respect to redundancy or tier confirmation, the design remains same. For example, with a conventional system where we have valves to do a job of balancing and modulation, let's say PABCV, pressure independent control and balancing valve. So you have multiple units. N plus 1, N plus N will have, let's say fan valve unit. You have N plus N fan valve unit with the valves. So just we are removing the valves and we are having a dedicated coil pumps. So it's the same design. The design remains same irrespective of it is a conventional valve based system or a dedicated coil pump system with respect to redundancy and with respect to tier confirmation.
Okay. Mr. Venkata Ravi wants to know how AI can be integrated.
That's a very good question, because even pumps or any device for that matter, we are moving digital. And one of the advantage of having smart pumps or intelligent pumps is that now we have a data. As I said, the smart pumps in the market, it has a sensor which can read all the data, like the critical parameters like the flow head, the power consumption, and those data can be used for further optimization using the AI algorithm if it is integrated with CPM. So that's the other advantage what we see when we move to a smart technology or intelligent pumps. Further optimization of the performance based on the live data is very well possible.
Dear participants, do we have any more questions?
Good. If there is any questions, please feel to reach the ISHRAE board, or this is my contact. If you have any technical questions on the design of this concept, I'll be happy to share more information going forward. And Mr. Manish, thank you so much. If we don't have any further question, I leave the floor to you to give a final words.
Surely.
Thank you. Thank you.
So, thank you everybody. On behalf of ISHRAE Conclave 3.0, I extend our sincere gratitude to Mr. Manimaran for sharing his valuable insights on optimizing cooling system efficiency with distributed pumping system in data centers. Your expertise and practical perspectives have made this session highly informative and enriching for all of us. We truly appreciate the time and effort you have taken to be with us today and contribute to the learning and growth of our HVAC and data center community. I would also like to thank a heartfelt gratitude to all our participants for joining us today, for your active participation and for making this webinar a success. Thank you once again for having a wonderful evening. Thank you.
Thank you so much for everyone. Have a good evening. Thank you so much.